Swayam Prabha. Digital India. Educated India.
In the last lecture, we saw the DFT phase shifting property. Today, as far as the properties of the DFT are concerned, we are done with it. We can directly move to the computation of phasor from discrete Fourier transforms or DFT. But there is one small connecting part which we will talk about today, and then move on to the computation of DFT. We may not be able to complete the whole thing today, but we will get started with it. This is the similarity between the at least mathematically between the fast Fourier transform and the n phase sequence transform. So, we will have a look at that, a very quick look, because it's to put it in other words, it's just of mathematical interest. We are not going to use fast Fourier transforms in this course. We are just interested with the DFT, and that too just the fundamental component that we will extract using DFT. We will get started with this lecture. First, we will start off with the fast Fourier transform and then look at the equivalence. We will, instead of just going through the slides, we will work it out on paper so that it is a bit more clear. So, this we will start off with fast Fourier transforms. The sequence transformation, of course, we have looked at it in a bit of detail. That was, of course, looking at it from a 3-phase perspective. Today, we will look at it from a more generalized n phase perspective, and then we will see the equivalence between the two. Okay. So, now when we write or when we our expression for DFT has been this is the expression that we have been using. You must all be very familiar with this expression by now. We also define if we define an operator, say A is equal to e raised to j 2 pi by n, which of course implies that 1 plus a square plus a raised to n minus 1 is equal to 0. Okay. So, this, and since now this expression can be written in terms of A as x of m is equal to sigma n is equal to 0 to n minus 1 x of n A inverse, since there is a minus sign there, raised to m n. Okay. So, what does that give us with m equal to 0? It will give us x of 0 is equal to, now here m is equal to 0 and n will vary from 0 to n minus 1. So, since m is equal to 0, all we will get is just a summation of these terms. Okay, for m equal to 1, x of 1 will be, now m is equal to 1 and n will vary from 0 to n minus 1. So, we will get 0 plus x 1 inverse plus, I am writing the second term also, so that it is a bit clear, x n minus 1, this is the last term raised to n minus 1, okay, and so on and so forth for x of n or n minus 1, because we have started from 0, we get x of 0 plus x of 1 here. In the second term here n is 1, but m is n minus 1. So, we will get n minus 1. Second term, third term rather, will be x of x 2 to n minus 1, so on, and the last term will be both m and n are n minus 1. So, we will get n minus 1 square. Now, if we write this in a compact matrix form, what we will get is this expression, x of 0, x of 1, x of n minus 1 is 1, 1, 1, and on this side you have the samples x 0, x 1, x of n minus 1. So, the second row from here we can make out is 1 A inverse okay. Here it will be A inverse square. Last term of course is 1 here, then A inverse n minus 1, so on to A inverse n minus 1 the whole square. Okay. So, this matrix if we denote as P or T or whatever matrix, earlier in the symmetrical component discussion we have used T, but now we are using P just for the sake of convenience, nothing else. So, here we get x is this the index of this vector is from 0 to say n minus 1. This is not strictly a matrix notation, but more of a MATLAB kind of notation. All of you must be familiar with that, and for this vector is also the same, the index is the same. So, x the length rather is n. Okay. So, this matrix here is what is called is the transformation matrix. Okay. This is what we will call a linear transformation. Why is that? What is the inverse of this matrix? So, if you notice here, the inverse is pretty straightforward to find, that the rows and columns of this matrix, the matrix P, are orthogonal to each other. What does that mean? If I take any xi, it is 0. Okay. If any xi, if it was a real matrix, of course, we would have got xi transpose xj is equal to 0, but since these are complex numbers, we have to take a conjugate also. So, xi transpose conjugate xj is equal to 0, which is nothing but x Hermitian xi Hermitian xj is equal to 0. So, now this due to this property we get some nice results. Actually, the property of orthogonality means that the axes are coordinate axes are orthogonal to each other, which gives us some nice properties which we can exploit. The inverse will be the the property that we will get is this. Okay. So, because the rows are only orthogonal, they are not orthonormal to each other. If the length was 1, then we would have got even better property to exploit, which is P Hermitian P is the identity matrix. But since the determinant in this case is not 1, but it is n, so we will get pH is equal to 1 by n is equal to, sorry, I will just write it a little more convenient location. So, pH is equal to 1 by n, and we will first do the transpose. So, the transpose of this matrix will write the first row and column first. So, 1 1 1 1 1. So, this is the same, and then this row here will go as the first column. So, inverse n minus 1, that column will go as the row. So, inverse is n, this is n minus 1, and so on and 1 square. Now, still have to take a conjugate of this. So, now what is, since A is 2 pi by n, so say inverse raised to some k, and conjugate of that is pi k by n conjugate, which is into k, which is a raised to k. So, the conjugate of A inverse of with the index k is a of k. Okay. So, this 1 1 1 1 a raised to n minus 1 1 a n minus 1 a n minus 1 square. Okay. So, as we said, because of the axes are orthogonal to each other, or these rows and columns are orthogonal to each other, we get a nice straightforward inverse here in this case. Okay. Now, this will also allow us to get the samples back, or the x small x of 0 to n minus 1 back. Okay. So, what did we have? We had x is equal to p small x. Okay. So, x is p inverse x, which is nothing but okay. So, we can write it, let us see what is the how this will look in the matrix form. So, we have x 0, x 1 up to x n minus 1 1 1 sorry 1 1 1 a a n minus 1, a n minus 1, a n minus 1 square into x of 0, x of 1, x of n minus 1. So, this is what we get from the inverse. Now, say suppose we want to get the kth row out. Okay. So, what will that be? X of k is 1 by n into 1 plus this is a raised to k plus a raised to 2 k plus a raised to k n minus 1, which is nothing but m k. Okay. In other words, okay. If you notice and remember our definitions from the last few lectures, this is nothing but the IDFT expression. Okay. So, what we have proved last time, we actually substituted and proved, but what we have now proved is an alternate proof of the fact that the IDFT exists, and this is the form of the IDFT. This also proves that this is an invertible transformation, and hence it is a linear transformation in its own right. Okay. Now, we will not as we said, this FFT is useful if we want to find the entire frequency spectrum. We are doing some power quality analysis where we need to say look at the various frequencies that are present in the, or harmonics that are present in the signal. So, there we will need to use the FFT. There are many applications of the Fourier analysis that we are doing. FFT actually this matrix, these matrices, this matrix and this matrix, the P matrix and the P inverse matrix, because of their unique structures will allow the computation of the frequency components or the frequency domain information to be computed in a very efficient way. Otherwise, if you look at the structure here and you want to compute all the n frequencies, the order of complexity is n square. Okay. And that is very computationally inefficient. So, it will take a long time, and you have a large number of samples. So, it could take an inordinately long time. So, to simplify that and exploiting the structure of this matrix, the algorithm to do that is known as fast Fourier transforms. Again, as we mentioned at the beginning of the class today, we will not be using fast Fourier transforms in this course, but of course, there will be other applications where we will need to look at the fast Fourier transforms. Okay. So, now we will look at having done this, what we are looking at here is just establishing the mathematical similarity with the n phase transforms. Now, for an n phase system, okay, this sequence transformation, say the symmetrical components will be the 0 sequence component, there will be a positive sequence, and then there will be n such symmetrical components. For a 3-phase system, there will be positive, negative and 0. For any other n phase system, the positive and 0 sequence will exist, and then there will be other components which will make up the n symmetrical components. Okay. So, we are more used to the dealing with the 3-phase system. So, we talk of positive, negative and 0, but even in a 4-phase system you will have 4-phase components. There will be positive and 0, and then there will be 2 in between. Okay. So, the sequence components, let us motivate it with the 3-phase example, and then we will extend it to a more general n phase. Okay. This is just speaking mathematically. So, we have say x 0 to x n minus 1, these are the components, and the 0 sequence is just the average of all. So, with that we can write in a very straightforward manner. Keep in mind that these are phasors. Earlier they were just samples, but these are phasors. So, they will be complex numbers. So, now the first 0 sequence is just an average. So, it is just the sum of the phases divided by the number of phases. So, for the second one, say we need to rotate the if A is equal to, in this case, 2 pi by 3. So, we need to rotate it by 2 pi by 3. So, this will be A, okay. And the second one will be 240 degrees. So, A square, in this case A n minus 1, okay, because n is equal to 3. Similarly, you will get for other components also. Okay. So, this is the sequence transformation matrix. If you notice, this is the same as our DFT was, this is the same P matrix or P inverse that we got earlier. So, we had DFT, we had, and P inverse x, which is, okay, this is the same P Hermitian. Okay. So, and we can just verify by plugging in our 3-phase example. Say instead of x, we can take say I, because we are dealing directly with phasors now. So, I0, I1, I2, which is the 0 sequence components of the current, and here we will get 1, 1, 1, 1, A and A square. Then we will get A, last one is A n minus 1 is A square, and then we will get A raised to 4 in this case, which is nothing but A, okay. And then we will get this should have been IIBIC, we are talking of currents, not of voltages. Okay. Since this term, since the A raised to n is equal to 1, the calculation of A raised to n minus 1 simplifies significantly. Okay. So, this is just that, this is our familiar 3-phase symmetrical component expressed in the matrix form, and we are very familiar, and we just verified it, or rather cross verified it. Though we are familiar with this three-phase form, the Fortescue's original paper, as we mentioned in the discussion on symmetrical components, was for n-phase systems. Okay, so this expression here is still, or is very much valid. It's only that we are more familiar with this expression here. Okay, now as we can see, mathematically they are the same. Okay, though application wise they are different. We don't look at it that way because or we don't develop the properties of the sequence transforms in the way that we develop the properties of the DFT, like phase shifting and symmetry and superposition and other properties that we discussed in the last few lectures. But here we don't develop the properties, because properties are developed keeping the applications in mind, and the applications of the application domain of the two are completely different. So that is why we don't look at it, but what we have just shown is that that mathematically they are the same transform. Okay, and this is just just to establish the similarity between the two transforms. Now we will I mean, we are not going to use, as we said, we are not going to use FFT in this course again, but that was just for the sake of completeness rather, that we discussed the properties. Okay. Now we will now move on to computation of phasors from DFT. Okay. This is what we are getting into the discussion on DFT, because we need to calculate the phasors from the samples that are made available to the relay, and then from the phasor we need to take the relaying decision. So this is actually the heart of computation for numerical relaying. So we will now look at it. Let us say that the signal that we have is x of t is equal to x of m, that is the peak value, cos of omega t plus phi, some general signal. Okay. Why we take cos is because it will directly map to the DFT. We can take xm sine of omega t plus phi, but then we will have to do some phase shifting, etc. So in some texts or some notes or some lectures, you will see sine. That is not, of course, that is not wrong, but it's just that it involves this is a less tedious way, let's say. So this is, so because we are expressing it in the RMS form. So I I mean, it's just a matter of scaling, root 2 of x cos of omega t plus phi. Okay, now what is the we are talking of n samples in one period. So if Ts is the sampling time, then nTs is equal to t, and what is the nth sample? X of n is cos of 2 pi n delta t upon n delta t plus phi. This is our sample number n. Okay, we are just talking of some in general some n number of samples. Okay. Now what is our DFT expression? X, we will first write the general expression, and then we are looking at calculating the fundamental frequency phasor from this, because that is all that we are interested in. We are just interested in actually this here, x of t can be expressed as, this is of course the real part only. So e raised to j omega t plus phi, okay, which is real part of x m e raised. What we are doing here is we are assuming omega is equal to constant. Okay, so our job is of now left to calculate x m and phi, or x and phi, depending on what what you are looking for, whether you are looking for the peak value or the RMS value. Okay. Later we will see after a few classes what happens if omega is not, if omega changes and then leads to DFT leakage and other things. Okay. So, now basically we just have to calculate x m and phi from for this signal here. Okay. Now, what is our DFT expression? Here, though we have not used it earlier, okay, we are using this constant here. We will soon realize why. As we said, we can use any constant as long as the inverse, we are adjusting it in the inverse DFT itself. So, C1, C2 are constant, where C1, C2 is should be equal to 1 upon n, where C1 is the DFT constant for the DFT, forward DFT. I am using the word forward as a layman's term, and C2 is the constant for the inverse DFT. So, though we have not used it so far, we are now using 2 by n. So, x of 1 for the fundamental frequency phasor is just 2 by n is equal to 0 to n minus 1 x of n okay, which is nothing but and just for the sake of convenience we will write it as, since okay, since this involves the first term involves a cosine term, we will write it as xc, and the second term, since it is a sine term, we will write it as jxs. Okay. Now, what is xc? And xs is the same, but with a sine term. Okay. Now, we will find out, and what is the xn? Xn is what we have earlier seen here, just this is the xn. Okay. So, now we will plug that value of xn and find out what xc and xn evaluate to. Cos of okay. Now, what is cos A, cos B? It will give me a cos of, or rather 2 cos A cos B. So, we will take this out, root 2 and x out, and we will get, well, you will get a cos of A plus B term and a cos of A minus B term. Okay. So, this is cos of this is A and this is B. So, cos A cos B. So, we will get cos of A plus B will give us 4 pi n by plus phi plus cos phi. Okay. Now, what is this term? So, a double frequency term summated over a full time period. As we saw in some classes, this is our time period t, and this is a double frequency term. If you sum it over an integral number of periods, time periods, the answer will be 0. So, this term evaluates to 0, and this term is just cos phi, it is a constant summated over n times. So, that will give us x to n cos phi, this n and this n will go, and we will get x c is equal to root 2 x cos phi. Okay. Similarly, for the excess term, we will just evaluate what the excess evaluates to 2 by n sine of what is our x n? Same as last time. So, we get root 2 x cos of 2 pi n by n plus phi sine of 2 pi n by n. Okay. So, we get instead of cos A cos B, we get sin A cos A sin B or sin A cos B, what the way we put it. So, we will get the same thing. So, 2 sin A, rather 2 sin A sin B. So, we will get root 2 x by n this is outside. So, we will get since we have taken sin A cos B. So, this will be A and this will be B. So, A minus B will give us minus sin phi. Similar arguments as last time, this term will, this is a double frequency term, sinusoidal term summated over a full time period will give us n, will give us 0, I am sorry, and this term will give us minus sin phi summated over n times. So, it will give us this is 0. So, this gives us n. So, it gives us so x c you will give us root 2 sorry minus of our thing was this. So, minus of minus root 2 x sin phi is equal to root 2 x cos phi plus j sin phi. Let me write the bracketing a bit correctly. Okay. So, this is what we wanted to find out, isn't it? When we so x and phi. So, we wanted to find out root 2 x cos phi plus sin phi. So, this x c minus j x s will give us the original phasor. Okay. So, this is our DFT computation. Now, there is just one small not a small this we were talking of n samples, some n samples that were presented to us, and we calculate the DFT from it. In a real life situation, what you will have is the samples coming in continuously, and we will have to perform this DFT calculation on a moving window. Say for example, you have you have a 12 sample window. Okay, so you have the first 12 sample, then 1 or 0 to 11 say, then you have the 12th one coming in, then you have the 13th. So, the first window is this, okay. It is a 12 sample window, then the second window will be this. So, these are there are 12 samples and then the third window is this. Okay. So, windows can be numbered. We need to know that window number to to calculate the DFT. So, the windows can be numbered with the first sample in the window or can be numbered with the last sample in the window. So, these are the one of the two conventions that will be followed. If the first sample is used, then this will be window number 1 or window number 0 in this case, then this will be window number 1, this will be window number 2 and so on. Okay. So, the window we have taken the convention that the window number takes the number of the first sample in the active window. Okay. Okay. So, now instead of the samples being simply x n being the sample, we will take the next sample as x n plus w, because we have the window number also to take care of. So, x n plus w will be so here instead of sorry, not this, there is no sigma in this. Instead of the x n being this, x n plus w will be because you have changed the index here. So, here this also will become n plus w. Okay. And just to distinguish, we will denote the cosine and sine components as x. Mind you, this is not omega, this is w. So, I will write it maybe slightly differently, and excess of w. Okay. This is the window number. Okay. So, your phasor now will be defined by x of 1 or x of 1 w is x c w minus j x s w. Now, what happens to the phasor calculation? We will just have a look. We just have to instead of substituting x c of w give us and x s of w on the other hand will give us okay. Now, x n plus w we just calculated what it is. So, that will be root 2 x cos of 2 pi by n plus w plus phi into cos of 2 pi n by n. Okay. Now, if you notice here, we have a 2 pi n by w term. A minus b, a plus b will still be a double frequency term. So, we will get, so 2 cos a cos b will still give us root 2 x by n is equal to 0 to n minus 1 cos of 4 pi by n plus 2 pi n plus phi 2 pi w plus phi, and the cos A minus cos B term will give us this term here. Okay, this term will still equate to 0 because it is a double frequency term summated over a full time period. So, what we will get instead of is n cos of w plus phi. Okay. Similarly, our excess term will also give us, this will go of course, I can write it directly, but anyway since I have written an n, sine of this is a minus sign here, sine of 2 pi by n w plus phi. So, x c minus for a moving window kind of algorithm, we will get root 2 x cos of, we can take this in bracket, cos of 2 pi w plus by n plus phi, because this is minus j xs. So, we get plus sine of 2 pi n w plus phi. So, now we get root 2 x e raised to j 2 pi n w plus phi instead of just e raised to j phi here. So, which this is our phasor that we desire, but we are getting an extra term here. Okay. So, what does this imply? Suppose we have got 12 samples per cycle. So, 2 pi n by 2 pi by 12 is 30 degrees. So, what it means is that for every window increment, this phasor will rotate by an angle of 30 degrees. Okay. So, this is not desirable. The phasor itself is not changing, this is not the phi. Okay. The phasor is even if the phasor is constant, the it will appear to be rotating because for every new window it has been incremented by 2 pi by n, okay, for every new window. Okay. So, this is that extra expression that we are getting. How to get rid of this we will see in the next class.